All right, in this next clip, we're going to take a look at how you handle circuits where the resistors are wired in ways that are actually neither in series nor parallel. So clearly these three resistors are not in series because they're not all along the same line, but they're also not going to have the same voltage drop across them. So I remember when I first learned this stuff, I thought I had the world conquered after learning series and parallel and combinations. But I remember a freshman year a professor writing this on the board, and then I realized I couldn't do it. And so we have to approach this with a new way. The goal here is to try to figure out how much current goes through each resistor. And so there's a little approach that we're going to take that will let us solve for the different currents. Well, so the first thing you have to do is decide how many currents there actually are. And in this case, there's going to be three. And the way to tell that is as any segment of wire along which there aren't any branches, there's no forks in the road, then the current's going to have to be the same along that entire length. So for example, this from here all the way to here, the current has to be the same throughout because along this segment or this chunk of the circuit, there's no forks in the road. So what we'll do is we'll call this unknown current I1. Now I would guess that it flowed that way because of the way that battery is oriented. Okay. Then this on this side, there would be another current that runs around this way. I'm going to call that one I2. So you can see I have a second unknown I2. And then these two currents are going to come in together. And so now this kind of forces our hand with which way this goes through the center, right? A little pitfall with this is what you don't want to do is guess that the the currents all kind of converge to one point because that's like a physical impossibility. So now that we've got current 2 flowing here and 1 flowing here, now we're actually committed. We have to decide that the current this way flows up through the middle. Okay. So here are our 3 currents. And what you can do next is, so we have 3 unknowns. So we basically need 3 equations that relate the 3 unknowns. The first equation you can get actually by looking at the junctions. And junctions are places where the currents might come together. So for instance, this is a junction. So if we look at a junction, what we can learn at that junction is, well, current 1 and current 2 conspire to make current 3. So a relationship you can get between the currents there is I1 plus I2 gives you I3. So that's at the junction. So we need 2 more equations since we have 3 unknowns. Now if you look at the top junction, there's one more junction in the circuit. Here you'd have I3 coming in and becoming I1 and I2. The problem is we already have an equation that relates the currents in that way, so that's not any new information. So we have to do something else. And so the something else is what's called Kirchoff loops. So sounds fancy, but all it is, so let me write it first, Kirchoff loops. What happens is anytime you walk around from one place and go around a loop and come back to the same place, what happens is the sum of any changes in voltage has to add to 0 by the time you return. So for example, suppose I started here and I walked around this right-hand loop and I checked all the voltage changes. Well, the voltage here is a certain value. I don't happen to know what it is, but it's some number. And it will change again, and then change again. But by the time I come back to the same place, it has to be whatever it was when I started. So this is going to be true around any path that you choose. And so what I'm going to do is start here and we'll name this loop over here. Well, let's call it A, B, C, D, A. A, B, C, D, A. So if we do loop A, B, C, D, A, right? So what we're going to do is go around this loop. The first thing we hit when we go from A to B is we climb over this battery. We go from the negative end to the positive end. So the voltage change, the first voltage change we meet is to go plus 5, right? So we go up by 5. me zoom out a little bit. That's about as far as I can go. So we go up by 5. Then we're going to have a voltage drop because we're going with the current across the resistor. So the voltage drop is IR. So it'd be like I2 times 6 IR. Just for style, I guess, I'll put the 6 as a coefficient. But it's really just IR. That's the voltage drop across the resistor. And then by the time you get here, it's going to be minus, again, IR, I3 times 4. Again, for style, I'll just put it in front like this, minus 4I3. And the sum of those voltage changes, climbing up 5, down by 6I2, and down by 4I3, those voltage changes have to add to 0, and that's our second equation. The third equation you could get by either going all the way around the outside, you could do that, or you can do what we're going to do here is just take around this little baby loop on the left. So if we do, here's A, I already got up to D, so let's go EF. Well, my phone had run out of memory. I guess that's what I get for keeping all my Philippines and India pictures on the memory card. Anyway, just to pick up where we left off, we'll just pick up that left-hand loop. So if we do now, we'll go loop AEFD. So let's do that. We'll write loop AEFD. So we just need to get AEFDA. We have to come back to this place where we started. So let's do that. You can see the first thing that we do is we climb up 3 volts. So that'll give us a 3. We go down by 2I1. So again, the voltage drop is IR, so minus 2I1. And then we go down by 4I3 again, minus 4I3 equals 0. So what you can see there is we have 3 equations for 3 unknowns. So there's number 1, number 2, and number 3. So we used 2 loops and 1 junction. One little possible, so this, by the way, all the physics is done. Now this is just a algebra problem like pre-calc or algebra 2 whenever you learn to solve 3 equations for 3 unknowns. This is going to work because these are 3 independent equations. Little possible pitfall is somebody might have thought, what if I did the right-hand loop, the left-hand loop, and the outer loop? The problem is the equation for the outer loop, say, you could derive from the equations for the other 2, so you wouldn't get 3 independent equations. Here we do have the 3 independent equations. Again, what we did is we looked at the currents at the junctions. At this junction, current 1 plus current 2 made current 3, and then we summed up the voltage drops as we walked around a loop and set the voltage drops to 0. So now again, the physics is done. Now this has basically just become a math problem. So what I want to do here, you could just do substitution and solve for the 3 variables that way. What I want to do is just remind you of how you set it up using matrix algebra. It's actually faster once you get into these a little bit. So just to burn through it super quick, like the top equation is I1 plus I2 makes I3. So your 3 unknowns are I1, I2, I3. So I'll just rewrite it like this. We'll say I1 plus I2 minus I3 equals 0. So I'm putting all the terms of the variables on the left. Second one, we don't have any I1s. We've got minus 6I2. We've got minus 4I3 equals, then let's put that constant over here on the right. So that 5 will go over here and become a negative 5 equals negative 5. And then finally, this last one, we do have I1s, so we got minus 2 I1. We've got no I2s. And then we've got minus 4 I3 equals negative 3. So the way it stands now, you've got these 3 equations. If you remember from pre-calc, maybe you learned from Miss Falcone, what you do, right, is just peel off the coefficients. So you got 1I1, 1I2, negative 1I3s. You don't have any I1s here. You got minus 6 of those. You got minus 4 of those. You got minus 2 I1s, no I2s, minus 4 I3s. And then that's going to be that times I1, I2, I3 equals 0, 5, negative 3, 0, 5, negative 3. So if you remember how this goes, what we would rather have is I1, I2, I3 equal some stuff. Instead, we have a matrix times I1, I2, I3 equal some stuff. So what you want to do, like in a calculator, is call this thing over here matrix A. So you have matrix A times I1, I2, I3 equals a matrix B. I'm going to leave a space. I'm going to put this over here, call it B. Then if you remember, what you want to do to solve this is just plug into a calculator an inverse matrix. So you want to do A inverse of both sides. And that will spit out, the calculator will just spit out the answers. So very cool. If with a circuit with only 3 unknowns, you could handle it just with algebra, with substitution and whatnot. But believe me, if somebody's working at Qualcomm, they're going to have more than 3 currents or something in their circuits. So they're going to have software that basically effectively does matrix algebra to solve systems of many equations for many unknowns. So now we can type this into a calculator to wrap this up. All right, let's go ahead and solve this thing with a matrix calculator. I actually realized that I made an error here on this page. This number here needs to be a -5 to match the work that we just did a second ago. So now let's go get this on the. I'll use one of these TI calculators since I think that's what you're mostly used to. So what you want to do is starting from the main screen, hit second matrix. So go in, and then what you want to do is edit the matrices, calling this matrix A and this matrix B. So let's put this guy in for matrix A. So what we want to do is edit matrix A. So I'm just keying over to that. And we want to make it a 3 by 3. Hit enter there. So now it's a 3 by 3. Let's zoom in a little bit. So matrix A is a 3 by 3, and we want it to look like this. 1, 1, minus 1 across the top. 1, enter, minus 1, enter. Then what do we got? 0, -6, -4. So let's go 0, enter that one. -6, enter. -4, -4, enter. Now let's do, what do we got? -2, 0, -4. -2, enter, 0, enter. -4, enter. So that one's all set. So let's get out of there. Second quit. We'll go back in. Second matrix, just to go back into that. We want to now define matrix B or edit it. So let's edit matrix B. Let's see. I always forget if these are 3 by 1s or 1 by 3s if we have a column like that. Does it go row column? Every time I forget this. So let's just see what happens. 3 by 1, it's row column. So then we got to make this 0, -5, -3. So 0, that one's good. -5, that's good. And -3, enter. So now matrix B is defined. So now let's get out. So we'll go second, quit. We're out of there. So now what you want to do, and you can see if things are keyed in there from way you did this before, but what you want to do to make this calculation is you want A inverse times B. So what you do is you say second matrix, and then what we want to do is just get matrix A. So all you have to do is just immediately hit enter. So there's matrix A. You just hit the X to the -1 button to do the inverse matrix, and then you'll just do second matrix and then go pull out matrix B, which I think you can get just by hitting the number 2 right now. So there's A inverse B, and you hit enter. And so you get these numbers, A inverse B, which is actually, bam, those are all your currents. They all came out positive, which is a sign that we guessed them correctly. And then just to idiot check it, we should see that I3 happens to be the big one. So let's go back to the original assumptions we made. And what you see is, let's try to get this all on the same screen. So it looks like, yeah, current 3 is like 0.636. That's the biggest one. Current 2 is second biggest. That's this one over here with the 5-volt battery. and then current 1 is actually the smallest. So those are the correct answers. That's just a way to set it up. Could have done it with algebra, but kind of nice to be able to do it with matrix algebra. And after you get used to it, that actually gets a little bit faster. Well, so thanks for tuning in. That's how you handle Kirchoff loops. Give the one on the next page a try. What is it, 34 or 35? Let me take a quick look. Yeah, it looks like on 34. If you feel like flexing, you could even set up the one after on page 30, 35. When you do get to this one, which is the next one that's on page 34, just as a little hint. So it's very similar to the one that we did, but the way these batteries are set up, you can see that at least one of these batteries is going to get not get what it wants. The current's going to get shoved back in its face. You can't have all 3 of these batteries happily pushing the current this way, because then that would converge here and that would make some kind of a black hole scenario. So when you're trying to guess which way the currents run, just don't make a guess that's impossible, meaning that all the currents rush to one point or that all the currents magically spring from a point. So what you're going to have to do is make at least one of these batteries unhappy. It's going to get it in your face when from the current. So don't worry about that. Just get it set up and then try to follow the process that we did on the when we set up the previous example, and should be good to go. All right, good luck. Catch you later.